So I am the forecaster at Portuguese Meteorological Service, as Dominic said. And so is my colleague Bruno that will also present today. Thank you very much, everyone. So let's moving on. So I will talk about the current situation, the current weather situation, and I will start with an overview using the upper levels. So in this case, the water vapor 6.2 satellite image. And with the water vapor image, we can check several things like the position of jet stream, moisture and dry boundaries that can be areas of convection initiation. We can also check dry areas that can be dry descending stratospheric air with high potential vorticity. And also we can, with the water vapor image, we can also check possible model errors. So today here with isotachs at 300 and geopotential at 300, we can see here at 6 UTC a persistent high over a low pattern over Europe that is dominating all Europe, with a high pressure system over northern parts and several low geopotential heights in the southern part and Mediterranean. Iberia, which has been mainly under the influence of a high pressure system in the early week, is now also under a trough that had a retrograde trajectory from the northeast. We can see in the yellow lines the jet stream further north and further south, which is typical in this blocking pattern that can also be called a diffluent block. Over the Atlantic, there is a trough near Azores, and we also have a short wave near Morocco. So an high over low pattern is one of the types of blocking. It's the type of blocking that there is a split in the eastwards flow. A blocking pattern, due to its stationary behavior, can lead to extreme conditions, especially related to temperature and precipitation. And as you know, there were huge amounts of precipitation in the past week in Central Europe with devastating consequences. So, of course, there were other ingredients, but the stationary pattern was one of them. So let's continue with the Airmass RGB, again with checking the upper dynamics. And also we have here the mean sea level pressure, so we can also have an idea what is happening at surface. So the high over low is dominating Europe, and we can see the warmer air mass, so the greenish colors over southern part of Europe, and the colder air mass, the bluish colors, going north over Northwest Atlantic, and then also in the northeast part, so the eastern part of the high level pressure. So there is a deep low level pressure system northwest of Azores. There is also a cloud band associated to this deep low level pressure system. It's not moving easterly. It's going to stay here for at least the next day or so. It's not moving very fast towards east. And also there is, we cannot see very well, but there is still a cold front, more or less stationary over the Azores Islands. I will show it better with another RGB. So west of Iberia, we can see a low level pressure system. And we also can see at this time of the day, so this is 6 UTC in the morning, we can see already some deep convection over central Mediterranean, Northern Africa, south of Iberia, and the eastern part, so on the right side of the image. And also there are some brownish colors that you can see that could represent some potential vorticity anomalies. So they should be monitored in the next hours. Let's go to the surface level. So now we can see the surface levels with this RGB. So with water vapor and air mass, we couldn't have much information about surface levels. So with this stable situation over Northern Europe, we would expect some fog and low cloudiness or very low cloudiness. And of course, we can depict them. And with the natural color RGB on the right side, you can see the thick water clouds are whitish, but the thinner water clouds have a more of a reddish tone. And we can see the low level clouds, so the thinner water level clouds over sea, in the Northern Sea, parts of Germany, Denmark, Baltic countries. And also we can see some low level clouds or fog in Norway, and it seems it's in the valleys. And so lots of areas with low level clouds or very low level clouds, and of course some fog. And on the left side, it's the night microphysics RGB, and the low level water clouds appear in pastel colors, and we can see them west of Ireland. Also, the convection areas I mentioned before, with a thick cloudiness and white with ice particles, and you can see the ice particles with the cyan color, so this bluish light color. And on the right, this is on the right side, natural color RGB, but on the left side, the image, we have the red color, meaning these are high opaque clouds. You can see them over the part of northern Africa. We can also see some contrails. So these contrails are high cirrus clouds and are dark blue or black. And we can see north of Azores. So it's like that kind of stripe cloudiness. And the frontal cloud zone near Azores, I told in the previous slide, appear here pink, which means it's a mid-level cloudiness in the night microphysics RGB. And there could be some showers today in the Azores Islands. And also the low pressure system have some clouds and frontal cloud bands. And here we have some different cloud layers. We have some water clouds very low, but also another layers with mid-level clouds and also high-level clouds with the red colors. So let's zoom in to take a big picture of the convection area in the Mediterranean. So this is very early in the morning, and we can see already deep convection with its enhanced infrared, with cold cloud tops in these three areas. And I overlay with Cape, and we can see exactly some areas of instability already here in this, mainly these three areas, the Morocco and Northern Africa, Italy, Adriatic Sea, and the Black Sea. And they will continue in the next hours. Also, we have here the lift index from Nowcasting Staff. Remember, this product is a clear sky product, but at this time, it was early in the morning, we can see already areas with some negative values. So these bluish purple colors indicate areas that we, again, we should monitor in the next hour. And already lots of lightning from the Euclid network, and the convective rainfall rate from nowcasting south showing already some high rates over these two systems near Iberia and central Mediterranean. So this area is, of course, an area of interest, and the warnings show exactly that. We have these warnings for today: thunderstorms and rain and flooding, showing several places south of Europe under yellow and orange warnings. The red one is for flooding. So the main threat will be high rainfall amounts, mainly due to stationary storms or slow movement storms. Another disturbance we should monitor in the next few days. So we still, although the recent forecasts have reduced the possibility of the storm heading for the Azores, but still the remnants of Tropical Storm Gordon are still in the central subtropical Atlantic, and in the next 48 hours, the chance of formation of tropical depression or tropical storm is about 20%, not very high, but is higher in the next 7 days, so like 40%. ECMWF also suggests a trajectory towards north, and with a very low chance of tropical storm intensity. Nevertheless, mainly for aviation and maritime purpose, we should also monitor this system. So the remnants of Gordon can be seen here. This is from yesterday at 15 UTC. So this is the cloud phase RGB from GOES East Sensor ABI. So this RGB will be one of the new RGBs from FCI instrument on board of MTG. And if you want to know more about this new RGB, you can go to the EUMeTrain webpage. You can see here, and you have the quick guide and also the extended guide. So the yellow star marked the area of convection. It was very disorganized yesterday and still is. But nevertheless, it seems that it's going to interact with a low pressure system that is northwest, and it may develop again in the next few days. Last, I want to show this extreme forecast index for 2-meter max temperature, showing maybe some higher than normal. At least the model is forecasting higher than normal max temperature for today in some parts of Northern Europe, not all, of course. But I think the stationary high pressure system is helping with this. And that's all from my side, the analysis for today. Thank you all. Stay safe. And Bruno, you may continue.
Good afternoon. So my name is Bruno, and I work with Ângela at IPMA, and I will now present. I want to show you the ongoing extreme wildfires event in Portugal, mainly in its north and center regions, and it started on the night of the 15th to 16th of September. It's a catastrophic event and that required help from several countries, namely Spain, Morocco, France, Italy, and has caused many victims, and an area of burned forest that is equivalent now to the size of 10 Lisbon cities. So to contextualize this situation, I'll make a brief resume. An high pressure system started to intensify near the British Islands around the middle of September, and together with a low pressure centered over Morocco, they were the main pressure features of the synoptic situation affecting the Iberian Peninsula. Later, another low pressure would develop west to southwest of Portugal, as Ângela showed previously. This allowed for very dry conditions to set in over Portugal, fueled by the eastern flow of a dry air mass advecting over Portugal. The pressure gradient also favored intense winds, mainly in the north and center of Portugal and over mountainous lands, especially during the night and morning. And these conditions started at the 13th of September and prevailed until today, with the most severe conditions set through days 16, 17, and 18. Here we have Airmass RGB for the 18th at 00 UTC. We can use this RGB to identify over Portugal a warm air mass with low upper tropospheric humidity. We have high brightness temperature values for water vapor 6.2 that inverted translates in a small contribution of the blue beam, representing high dry upper levels, and the mix of the green and red beam corresponding to a warm air mass. Leading to this event, we had a very hot and wet spring and a summer with some periods with temperature above normal in July and August, and some precipitation above normal in June. And here you can see the drought index, like PDSI, the Palmer Drought Severity Index, that is based on the concept of water balance, and it accounts for quantities of precipitation, air temperature, and water capacity available in the soil, and allows us to detect the occurrence of drought periods. Looking at the map, we can see that August ended with a drought situation classified as normal for the northern littoral region, weak in the northern inland, moderate in most of the central and south regions, and severe in the southeast region. Here we can see the scatterometer data from sensor HSCAT. It's on board the Chinese satellite, and this is for the morning and late afternoon of the 17th. On the left image, you can see the easterly flow over the sea at the northern part of the Portuguese coast. And this kind of flow is not the predominant one in this region. So this is a signal that the eastern flow is so strong that it reaches the western coast of Portugal, and in turn decreases the humidity over these areas to values well below average. On the right image, we have data collected for the late afternoon of the same day, and it shows us the last part of the temporary sea breeze period that set in. We can see the northwest winds during a short time period during the afternoon. Using the coastal scatterometer ASCAT on board METOP satellite, we can see data for the early night period of the 17th. And this scatterometer has a better resolution than the previous one. It has a 12.5 kilometer resolution and data closer to the coast. So we can easily see the eastern flow over the sea already establishing at the northern part of the Portuguese coast, setting the night for another period of low humidity values near the coast and preventing the humidity recovery usually expected during the night. Here we can see the ongoing fires in the 18th at 9 UTC detected through the Meteosat geostationary satellite on the left. We got a bigger picture with fires mainly active in the south of Africa, also Brazil, Portugal, and as you can see on the right side map, mostly in north and center of Portugal, but also in southern Galicia and Zamora in Spain. On the left, we have the fire radiative power, and it represents the amount of heat released by unit of time, and it's related to the rate of burning fuel. It's calculated every 15 minutes and then accumulated through the lifetime of the fire, and it allows for an estimation of the total FRP that is proportional to the total of burned biomass. This product is disseminated by Landsat project and contains information about location, duration, and power. On the right, we have the fire radiative energy is obtained after the FRP data and accumulated through a period of time that spans between 15 minutes and 5 days, and with the colors of the hotspots representing the released energy. And here we can see mostly showing top classes for Portugal. The night macrophysics RGB is well adapted to detect fires during the night and takes advantage of the temperature responsivity principle that says that for the same temperature change, the 3.9 has a higher change than the 10.8 channel in this case. So when fires are present, the green beam has the lowest value because brightness temperatures are higher for 3.9, and that brings that difference to 0. As the green beam has no weight in this RGB, the color obtained is a mix between red beam and the blue beam, and resulting in a magenta color as seen here, and that identifies the hotspot. Using the isolated channel of the infrared 3.9, you can see the pixels that identify very hot fires during night and day. And when the fires have very high temperatures, saturation occurs. In the image below, we can see the fire strangely invading the sea. The explanation is that when full saturation of the pixel happens, that affects the next pixels in the scanning line because the sensor has to pick a sample of photons very quickly, and as it scans to the west, it doesn't have time to desaturate. So the next pixel to the left is affected. That is called the blindness effect, and that is something we have to account for in these cases when using MSG. Here you can see that also that infrared does not detect smoke. You can see smoke in this channel. There is no scattering with the particles of smoke because they are very small. When the particles of smoke become bigger, they can appear, but with a weak signal. Here, Rayleigh scattering occurs due to the small size of smoke particles, and visible wavelengths are very sensitive to the scattering. So these smaller wavelengths used here have higher reflectance values, and larger wavelengths have lower reflectance values, and we can take advantage of that with this natural RGB. Also, using the difference between these natural RGB channels, it is sometimes possible to see that if the smoke plume is closer to the point of origin, we'll have more green color because it corresponds to the larger particles that travel less. And if it is further away, it will have more blue color corresponding to the smaller particles that can travel far. You can use this with this natural RGB, although in this image you can't see that. So that's why infrared wavelengths are not suitable to detect smoke, and the reason why the smoke was not seen in the infrared channel in the two previous slides. Now talking about near future and the advantages of MTG over MSG, it is possible to simulate the difference between SEVIRI and FCI sensors using a polar satellite with the sensor MODIS that have a similar characteristics to the FCI sensor. On the left, we have natural color RGB from MSG, superimposed by a fire temperature product based on the 3.9 channel of MSG. And on the right, we have a true color RGB, similar in resolution to the same RGB from MTG, and superimposed by a fire temperature RGB that uses channels similar in spectral and spatial resolution to the MTG channels. The true color RGB in FCI will use the 0.4, as you can see on the right, a new channel, the 0.6 and the 0.5 and the 0.6. And having the new channel 0.4 will provide a better detection of smoke plumes because of its smaller wavelength. This fire temperature RGB seen here on the right gives us an understanding of how the FCI RGB will improve over the SEVIRI one. The new fire temperature RGB will allow to identify better the different intensities of a fire because of better spatial resolution. When SEVIRI has 1 pixel, the FCI will have 9 pixels. Because of better radiometric resolution, the 3.8 channel will see most fires. The 2.2 channel will see fires that are more intense, and 1.6 will see even more intense fires. And this will permit a better intensity differentiation within the perimeter of the fire. Also, the new channel 3.8 has a higher brightness temperature saturation point, around 600 Kelvin. So it prevents the blindness effect we've seen in earlier slide, and higher sensitivity to subpixel fires. For more information about FCI, I encourage you to see the presentation by Andrea Mariner from EUMeTsat about the MTG FCI pre-operational work related to monitoring and visualization of wildfires. You just have to enter the EUMeTrain site, go to resources and search for the webcast. All right. Thank you very much for your presence, and we'll see you on the next weather briefing.